Okay, so Moira Venegas from USACH will give us a talk on relic density of axion dark matter in standard model and standard and non-standard cosmological scenarios. Go ahead, Moira, and I will let you know when you have 5 minutes left.
Okay, thank you. So I'm going to talk about relic density of axion dark matter in a standard and non-standard cosmological scenarios. This is the overview of my talk. First, a brief introduction of dark matter and axion. Then I'm going to explain what is a standard cosmology and how is the production of axion there. And finally, our proposal, which consists in considering non-standard cosmology. So more than 26% of the matter content in the universe has an unknown nature, and we call it dark matter. By astrophysical and cosmological observation, we know about dark matter must be cold, it means be non-relativistic and thus can explain the structure formation in the universe, and also must be invisible because the interaction with the ordinary matter is weak, otherwise would have already been observed. Since the standard model of particle is not able to explain the nature of dark matter, we need to go beyond a standard model, and a good candidate corresponds to the axion, which we classify as a weak interacting slim particle, or the abbreviation WISP. And the axion was initially introduced to solve the transit problem. The transit problem consists in the fact that the QCD Lagrangian allows a CPU latent term, which is given by this expression that I brought here, where G is the strength tensor of gluons, and the theta parameter has two contributions of different sectors. The first of them comes from the no trivial vacuum in QCD, and the second one is a contribution of the mass of the quarks. This parameter theta gives rise to an electric dipole moment for the neutron, but by no observation, its value is constrained to be lower than 10 to minus 11. So we understand the transit problem as a fine-tuning problem because these two parameters of totally different physics must cancel to a high precision. So a solution for the transit problem corresponds to the Peshay-Quinn mechanism. So the main idea consists in promote this parameter theta to a dynamical field, where A is the axion field. To do it, we need to introduce a new global symmetry U1, which at some temperature Fa is spontaneously broken. Then the axion emerges as an Nambu-Goldstone boson. Then when the temperature decreases and is similar to the temperature of QCD, no perturbative effects in QCD induce a potential for the axion, such that the axion starts to roll toward this new minimum, and the strength Cp is solved there. By this effect, the axion gets a mass. So now the axion is a pseudo Nambu-Goldstone boson, and the axion mass is inversely proportional to the scale Fa. Okay, what is the role of the cosmology in the axion physics? First, we need to know that the expansion rate is given by the Hubble parameter, which depends on the different contribution of the energy density that the universe has. And the energy density scales has a potential love with the scale factor, depending on what fluid we are considering. So for instance, for matter, the energy density scales as r⁻³ and for radiation as r⁻⁴, and so on. When I say standard cosmology, I mean that we are considering that the early universe is dominated by radiation post the inflationary epoch. So for radiation, we know that the energy density has this form, where G stars correspond to the relativistic degrees of freedom. And how radiation dominates the universe, the expansion rate is given by this expression here. And during this epoch, we have entropy conservation. And due to that, we have the relation of the temperature is inversely proportional to the scale factor. So now we can study the axion production by misalignment mechanism in a standard cosmology. So the equation of motion for the axion field corresponds to this one. Here we have the Hubble parameter, so it's given by radiation in a standard cosmology. And we can see that this equation corresponds to a damped harmonic oscillator, where the Hubble parameter acts as a friction term. For high temperatures, the Hubble parameter is larger than the axion mass, so we can ignore the last one. And the axion and the field evolves as a constant, which is given by the initial misalignment angle. This value corresponds to a free parameter of the theory, And we can see this behavior in this part of the figure. Then when the temperature decreases, the axion mass becomes the same order than the Hubble parameter. At that moment, the axion starts to oscillate around its web, and we can obtain the moment at which the oscillation starts, and we call it that temperature as Tos, and we can obtain it by equating these two terms. So that moment corresponds to this line here. Then, using the conservation of comoving axion number, we can obtain the present energy density of axion, and we can see that evolves as R2 minus cube. So the axion energy density behaves as a non-relativistic matter. Sorry, the axion behaves as non-relativistic matter. Then, using entropy conservation, we can rewrite the last equation and finally obtain the relic density of axion. So it corresponds to this expression here. We can see that depend of the axion mass and of the initial angle. And in our work, we want to consider that the axion, or we are considering that the axion can explain the whole dark matter currently measured. So we put this value here, and we can obtain a relation between the initial angle and the axion mass. So we develop this plot where in the blue line corresponds to the space where the axion can explain the whole dark matter. Above this line, we have an overproduction of axions. And below this line, the combination of parameters is not enough to explain the total dark matter. Okay, so our proposal consists in considering non-standard cosmology. The motivation to do it is because due to the lack of data, the cosmological history is supported from the Big Bang nucleosynthesis epoch onwards. And why study a non-standard cosmology using axions? Because I would trail of the history pre-Big Bang nucleosynthesis is the dark matter relics that we observe today. So we are introducing a new extrascalar field that achieves to dominate the energy density of the universe post-inflation. And we don't want to affect the observation in Big Bang nucleosynthesis, so we are taking that this field decays at some temperature T with a decay rate gamma. The equation for this new field corresponds to this one. So for that, the energy density scales as R in this way with the scale factor, where I'm calling beta to this exponent by simplicity, and beta is a free parameter. Okay, so we are interested in studying the axion production in this new period. With more details, we are considering as initial condition the ratio between the initial energy density of this new field and radiation. These are the Boltzmann equation for the fields. So we can see that this new field decays in radiation. And the equation for radiation is true if we consider the relativistic degrees of freedom as a constant, but we want to keep track of them, so we write this equation in terms of the entropy. Then now the expansion rate is different. Now has two contributions, one by this new field and radiation. And the free parameters of our theory correspond to beta related with the equation of a state of this new field, kappa, the temperature at which we are considering this new cosmology, and Tn. So this plot corresponds to the solution of the Boltzmann equation. Here I put energy density times the scale factor to 4, because in that way we can see when radiation behaves as like in a standard cosmology, or the usual way. And we can differentiate 4 stages in this new cosmology. The first one is when radiation starts dominating. Then this new field starts to dominate the energy density of the universe. The third one is when this new field is still dominating, but now the effect of the decay of phi is important. So that generates entropy injection in radiation, and for that the radiation change its behavior. The final stage corresponds when this new field is decaying and radiation still doesn't behave as the usual way. Finally, when this new field has already decayed, radiation starts to dominate the energy density again, and we recover the standard cosmology. Okay, so consider non-standard cosmology has two effects in the production of axions by misalignment mechanism. The first one is how, since we are changing the expansion rate, so for instance, this plot shows the change of the expansion rate in a non-standard cosmology in comparison with a expansion rate in a standard cosmology when radiation dominates. So in this plot, I'm taking different values for beta. So we can see that for a lower beta, the expansion rate is faster. And in this one, I'm taking different values for T-end. So for a lower T-end, the black line, we can extend the duration of this new cosmology.
5 minutes.
Okay, thank you. And how we are changing the expansion rate, the temperature at which the oscillation starts is different now. And so for instance, in this plot, the crossing with the grid line corresponds to the temperature at which the oscillation starts. And the gray line is for a standard cosmology, so the match is here. And the colors line correspond to a standard cosmology, but with different T-end. So we can see that for a lower T-end, we can retard the moment at which the axion starts to oscillate. The second effect is due to the decay of phi, there is an entropy injection into standard model radiation. It generates a dilution of the dark matter density. So if we write the energy density of the axion, we can obtain this expression, where the first part is similar to the expression in a standard cosmology, but again now TOS is different. And also we have this new factor which corresponds to the dilution factor and appears by this entropy injection. So finally, we can obtain the relic density of axion in this new cosmology. And this is a result that we obtained so far. So again, the initial angle in function of the axion mass. The blue line is for a standard cosmology. And the colors, the purple line is the space where the axion can explain the whole dark matter, but in a non-standard cosmology using these parameters. So consider a non-standard cosmology allows us move in this window, go to different combination of parameters. Okay, so finally, some comments. And I would like to say that a possibility that an axion discovery could be made in the next year help us to reconstruct the cosmological history of the universe prior Big Bang nucleosynthesis. Thank you.
Okay, thank you very much, Moira. Are there questions or comments? Patricio Scalona has a question in the chat box. Oh, comments. Great talk. Thanks.
Thank you.
Maybe I can ask a question. It may well be off topic. So when you talk about non-standard cosmologies, do you mean non-standard equations of state or non-standard cosmology with different gravitation theories of gravity?
No, I'm taking some fluid with some equation of state dominate the energy density of the universe. So yeah, different equation of state.
Okay,